So as far as calculus goes, we have pretty much covered the bulk of what you would see in a first semester course in differential calculus. We've talked about limits and derivatives, definition of derivatives. We found how to find derivatives, different differentiation. We've seen finding those principles to optimization problems, and then we also talk about related rates as well. It's another topic. And so now the final few things to talk about are just two particular kinds of functions. And I think you may have seen these before. So these are like this is like the last few things that we will discuss. So there are exponential and logarithmic functions. Is everyone aware, understand what exponential functions are, or is this the first time you guys hear of it? I know we've discussed, you guys have seen um, exponents, but do you guys know what exponential functions are? So exponential functions have this form. A times b to the x. Now a is what's called an initial value, also known as the y-intercept. And b is the base. Now there are two kinds of bases. So the first kind is that my b value could be between 1 and 0. So if my b value is between 1 and 0, I have what's called exponential decay. And if my b value is bigger than 1, then I have exponential growth. Now, exponential functions are particularly very useful in terms of modeling different physical phenomenon, such as population growth. Population growth is something that occurs that has an exponential growth. Particularly, we're living in a pandemic of epic proportions, and the way germs spread, right? Bacteria, the way viruses they spread is at a exponential rate. That's why we talk about doubling, how things double every few days, and what happens as the rise of number of cases increases, right? Exponential functions can model that kind of trajectory. Um, and there are other things too, such as the temperature change. That's also exponential in nature. How money grows in certain investments, um, uh, different kinds of what was called compound interest rates, right? There's an exponential nature to them. So understanding exponential functions is extremely useful in real world applications. One of the most useful functions we'll talk about. So So we have exponential growth and exponential decay. So what do they look like? Exponential growth. And again, my b value is bigger than 1. So when I graph it, I get something like this. And this crosses here at a. Now, what can you guys tell me about the domain? What's the domain of this function? And what's the range?
Wouldn't it be all real numbers because it's a polynomial?
That's right. It's not a polynomial, it's an exponential
Oh,
function. So
exponential.
yeah, this is an additional type of function. So we've been discussing polynomial functions this whole time. We've been discussing polynomial functions and rational functions this whole time. But now we're including one additional group, which are exponential functions. And you're correct. The domain is indeed negative infinity to infinity because this goes all the way to infinity and this goes all the way. So as x goes to negative infinity, my values here approach 0. As x approaches positive infinity, my values approach infinity. So then what would be the range? So what are the y values? How would I write the y values of this function? Bigger than 0. That's right, Fujin. So this would be from 0 to infinity. Again, the x-axis here, this actually acts as a horizontal asymptote. So this graph here gets really close, never crosses it. So it's like a boundary. So we also have what's called a horizontal asymptote. The horizontal asymptote is given by y equals 0, which is also known as the x-axis. Okay. And what else do we have? So we have this, and then we also have exponential decay. For example, the amount of carbon in an organic organ in a living organism or in an organism after it has died, right? The amount of carbon that exists behaves in an exponential rate. But of course, as time goes on, there's less and less of it. There's less of the the uh, the element, and exponential functions explain that again. So this is a times b to the x, but this is when my b value is between 0 and 1. And the curve is very much just like exponential growth, but it's going in the opposite direction. So actually it has very much the same attributes as exponential growth. So I'm gonna just erase this a bit here. Whoops. So here we have exponential growth and exponential decay. These are our two functions here. And what else do we notice about the graphs? Well, in particular, one is going up, the other one's going down. One is increasing, the other one is decreasing. So one major difference, right? So we note that exponential growth means that there's increasing. So the graph is increasing on negative infinity to infinity. And note that the graph is always decreasing. So this is always decreasing on negative infinity to infinity, and this is always increasing, always. Okay? Now, there's a very special number as a base that we use with exponential functions. And that base, so this is a special number here, special number. Used as a base for exponential functions. And that base is called Euler's constant. It sounds like you should, it looks like you should say Euler, right? But it's Euler, Euler, it's German. And this constant is given by E. And this is an irrational number. This is on par with pi. So the same way pi is irrational, it has an infinite decimal expansion that has no real pattern. E is the same way. And if you want to find what E is, let me just it's not working right now. Anyways, so if you want to find what E is, you raise E to the first power. You put this in your calculator and you get 2.71828. Blah, 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 blah. So 2.718. 2.71828, and this goes on forever. And this is a very special number because this appears a lot in nature, in the way the world works. E is a number that appears a lot. So this is a special number. Okay, so let's say I give you an example of an exponential function, y equals, let's say 2 to the x, right? So that's one thing you guys should notice, that what makes an exponential function exponential is that my variable is an exponent. And look at the difference between y equals 2 to the x versus y equals x squared. So what happens when the x's and the 2's are interchanged, are swapped? So what would be the difference? And let me switch this a bit. Let me call this f of x. What if my function is 2 to the x and I have another function here, g of x? So what do we have on the right? What kind of function do we have? I know it's early, guys, but it's not that early. What is this function here?
It looks normal.
What do you mean that by normal?
I know there's a word for this function, but
Yeah.
I forgot.
Really? So when you have a power to a 2, when your exponent is a 2, it's a, does anybody know? What do we use? What formula do we use when we have equations that have a 2 as an exponent? Starts with the Q.
Quadratic
It's a quadratic. So this is a
Wow.
quadratic function.
with just one number
Say that again?
with just one variable. That's it. It's just a quadratic.
Yeah.
I'm a bit surprised. Sorry.
No, don't be surprised. A quadratic function has this form, okay? This is the general form. Y equals ax squared plus bx plus c. This is a quadratic in its generality. But
Mhm.
if I just have an x squared, it's part of it. It's a part of this. You see that? The most important thing is that this appears. If you have an x squared and that's the highest exponent, the 2 is the highest exponent, it's immediately a quadratic. Immediately. Now, the difference here is that now let's say I switch these two numbers. What do I get? 2 to the x. And what is that going to be? It's no longer quadratic anymore. It's exponential. So it's different. Completely different. So that's the exponential. And then what kind of exponential function is it? Is it growth or is it a decay exponential function?
Growth.
Well, remember how we defined our functions. They're either growing or decaying based upon the base. Now my base here is a 2. And since the base is bigger than 1, it's going
Growth.
to be growth. Definitely. It's a growth function. And then what would the graph look like? What would the graph look like for each of these guys? Well, the graph here is a parabola, right? It's our this is one of those functions that you must know by heart. X squared. It's a parabola. And this function here is an exponential growth function. And it looks like this. We just drew it. And where does it cross? Where does it cross the y-axis? What's my initial value? What's this initial value right here? Does anyone know how do we can find that? It's 1. Thank you, Fujing. How did you find that? How did you know that this is 1? How did you know this is 1? You're right. It's 1. X equals 0. Perfect. That's right. So guys, to find the y-intercept, right? To find the y-intercept for any function, plug in x equals 0. So if I plug in x equals 0, f of 0 equals 2 to the 0 power. And anything raised to the 0 power is 1. So that's why it's 1. Okay? Okay. So let's look into exponential functions a bit more. What if I have a function that has this 10 to the x? What is f of 3? Well, f of 3 would be what? 10 to the third power. And what's 10 to the third power equal?
1000.
1000. What is f of 0 equal? 10 to the 0th power. But 10 to the 0th power is?
It's 1.
1. So there's a general note, okay? Make this a note. Note. Anything raised to the 0 power is always 1. You can call this the 0 power rule. The 0th power rule. So if you raise anything to the 0th power, you would always get 1. Now, what about if you plug in a negative number? What is 10 to the negative 2 power?
One over 10 to the second power.
Right. Negative exponents, right? You guys know how we do negative exponents. We make them positive by placing them underneath the radical, the denominator. So you're right. This is 1 over 100, which equals 0.01. Okay, so we have some kind of intuition, understanding of exponential functions and how we can plug in. So I'm not gonna go over that stuff so much in terms of how we evaluate exponential functions, but I do want to talk about what are called what is solving exponential equations. So I don't know if you've seen this. So what are solving exponential equations? So an example of that, we can start slow. So what if I have 6 to the 2x equals 6? Solve for x. Does anybody know how we can solve this? Wow, Coco, that's pretty good. Yeah, we're gonna talk about logs. So you could definitely log both sides, but there's an easier way. So you don't have to take logs in this scenario. You always can though, but there's an easier version of doing this without using logs. So you can actually solve this equation without using logs. Does anybody know? That's right, Fujing. Now, how did you get that? Well, what do we have on the right side of the equation? We just have 6, right? So we just simply have 6. So 6 is being raised to the first power. So whenever you have a number just sitting there, then it's the same thing as writing that number raised to the first power. Now, what do we have? We have the same base. So we're saying 6 raised to some exponent is equal to the same base, 6 raised to some exponent. So if both equations, both sides are the same, right? Then the implication is that the exponents must be the same. Same base, then this must mean that the exponents should also be the same. So that's why we have 2x equals 1, which means that x equals 1/2. And then normally what would we do? We would check. How do we check? We would say 6 2 times 1/2, is this the same thing as saying 6? Question mark. So I'm plugging it back into my original. And 2 times 1/2 is indeed 1, which is indeed 6. 6 to the first power is 6. So this works out. Of course, this is the easier kind of equations. Now, what if I get something that looks like this? 3 to the 3x minus 4 equals 3 to the 5th power. So again, same thing, right? Same base. I got the same base. And this is an equal sign, so this must mean that these are the same exponents. So then we got 3x minus 4 equals 5. We add 4, we add 4. 3x equals 9, so this means that x equals 3. Done. I solved my equation. X equals 3. You want to check, put it back in. If you plug back in the 3, 3 times 3 is 9 minus 4 is 5. 3 to the 5th power is 3 to the 5th power, so it works out. It works out. X equals 3. You all see that? Okay, now what happens if I get something like this? And I want to solve for x. What happens here? Use different numbers. What do you mean by that, Coco? What do you use different numbers?
Can you say 2 to the third to the x, and then you have to rewrite the other side?
Yeah, that's right. To what? Well, what do we write? Rewrite the other side to? Huh. So that's very good, Coco. So you notice that you're like, wait a minute, 8? I can rewrite. So far, the difference between this equation and the previous two, right? The previous two equations, we had the same base. So it was all good. Now you look at this one, you're like, whoa, what the? You have an 8 and you have a 1 over 32. That's definitely not the same base. One's a fraction, the other one's a whole number. And they're not even the same, apparently. Now, Coco, you made a good observation. 8 can be rewritten. So I want to so the idea here, the idea, so the idea is to rewrite bases. Rewrite bases to make the bases the same. So then you notice, wait a minute, 8 is really 2 to the third. That's true. So 8 is a power of 2, right? 8 is a power of 2. Now the question is 32 also a power of 2? So if I have 1 over 32, is there some way to rewrite 1 over 32 as a power of 2? Does anybody know how to rewrite 32 as a power of 2? Coco, that's good. So 32 is also 2 to the 5th power, but in this case, we're going to want to have our negative exponents. because I want to write it as 2 raised to some power, not 1 over 2 raised to some power. So this will be 2 to the negative 5th power. So actually, 1 over 32 can be rewritten as 2 to the negative 5th power. So now I have a rewritten equation. What's my rewritten equation? I can write a to the x as 2 cubed raised to the x. And I can rewrite 1 over 32 as 2 to the negative 5th power raised to the x minus 2 power, right? And now what do I do? Now I have the same base, don't I? 2 is the base here, and 2 is my base here. But now what do I have to take care of? These exponents. So how do I take care of these exponents? So remember the laws of exponents.
Can you multiply them?
Of course. So let me just say, just make sure this is extremely important. Laws of exponents. This is something that you've seen in Math 115. But just as a little quick review, let me write this as b. B raised to the m power times b raised to the nth power is b raised to the sum of the exponents. If you have b raised to the n power over b to the nth power, this is the difference of the exponents. And if you have b raised to the mth power raised to the nth power, this is the product of the exponents. So in this case, I can rewrite this as 2 raised to the 3x, because 3 times x is 3x. And then I would say this equals 2 raised to the negative 5th power times x minus 2. So I multiplied negative 5 with x minus 2. And I get 2 to the 3x equals 2 to the negative 5x plus 10. So these are the same, right? The 2 is the same base. So it means that the exponents must be the same exponents. It's the same base. And then I have the same exponents. And the exponent's going to be 3x is equal to negative 5x plus 10. So then I can solve this. I'll solve this and I get 8x equals 10, which means that x is equal to 10 over 8, which means that x is equal to, if you divide by 2, you get 5/4, which is the same thing as saying 1.25. Okay, so you have to know your powers. Your powers of 2, you have to know your powers of 4, powers of 3, powers of 5. Be able to recognize what numbers are powers of what other numbers. And let's do one more of these. Okay. What happens if I get 3 to the x minus x squared equals 1 over 9 to the x? So 3 is already, you can't rewrite 3. 3 is 3. You can't rewrite 3 as a number of a base that's smaller. But what about 9? How can you rewrite 9? So 9 can be rewritten as what?
Three squared.
3 squared. So then I can rewrite this as 1 over 3 squared to the x. And then this becomes 3 to the x minus x squared equals 1 over 3 to the 2x. So far, look, the same bases, but one is a fraction and the other one is not. I don't want fractions anymore. So then what do I say? How do I take care of that?
Can you write it as a negative?
Correct. So what would it look like instead?
It would be 3 to the negative 2x.
3 to the what?
3 to the negative 2x.
That's right. So this would be 3 to the negative 2x. So now I have the same base, which means if I have the same base, then I must have the same exponents. Where are my exponents? X minus x squared equals negative 2x. Now look what I got. What do I have here now? What kind of equation is this? We've seen tons of these.
Quadratic.
The quadratic, how do you solve quadratics?
Factoring. Putting everything on one side equal to 0 and factor.
Right, so quadratic equations, I want to solve it. So this is going to be, if I put everything on one side, I can rewrite this as x squared minus 2x minus x equals 0. So this is going to be x squared minus 3x equals 0. You can factor this, x minus 3 equals 0. So then you get x equals 3 and x equals 0 as two solutions. So in this case, you have two different solutions, and if you plug it in, x equals 0, you get 0, 0, right? 3 to the 0th power is 1, and 9 to the 0th power is also 1, so 1 equals 1, that works. And then if you plug in 3, so you get 3 minus 3 squared, which is 3 minus, so yeah, let me do this one for you. So x equals 0 works immediately, but what if I want to check, if x equals 3 works. So then I have to plug it in. 3 to the 3 minus 3 squared. Does this equal 1 over 9 to the 3rd power? So that's what they're asking. And then this becomes 3 to the 3 minus 9. Does this equal 1 over 9 cubed? And then this becomes 3 to the negative 6 power. Is this 1 over 9 cubed? So then you're asking what is 1 over 3 to the 6? Does this equal 1 over 9 cubed? Can anyone tell me? Is this true? 1 over 3 to the 6 is equal to 1 over 9 cubed? I mean, we can check it with our calculators, or we can notice that 9 can be rewritten as 3 squared cubed, which is indeed 1 over 3 to the 6. So this is true. So this is good. Okay. So that's logarithmic functions. I mean, exponential functions and how we can solve exponential equations. So now, wait, actually, there's one more kind. There's one more kind. Yeah, there's one more kind of equation that I want to show you guys. And this is if I have something like this. So what if I have 3 to the 2x minus 12 times 3 to the x plus 27 equals 0. Now look at this. This looks kind of crazy, doesn't it? So what do we do with this? We run away.
Wouldn't you have to rewrite it?
How do I rewrite it?
So you have to get all of the same bases. They're all multiples of 3. So you're gonna have to write 3, like the 12 as 3 to the power of, I don't really know.
Yeah, 3 is not a power. It's a multiple, but not a power of 3.
Not
So
a
that's a
power.
big difference.
Okay.
12 is
So
3 times
maybe,
4, but you can't write 12 as 3 raised to some power only.
yeah.
27 you can. 27 is 3 cubed. But actually we have to do something a bit more. So if you notice, this is actually a quadratic. I know it's kind of weird to say this, but this is an exponential function kind of disguised as a quadratic equation as well. You see why. 3 to the 2x, I can rewrite this as 3 to the x power squared, can't I? And then I
Yes.
got minus 12 times 3 to the x plus 27 equals 0.
Mm-hmm.
Then what do you notice? I got 3 to the x. I got 3 to the x here. So then look what this is a technique that we do. We use like a u substitution. So what if we say our u substitution is that we say u is equal to 3 to the x. So wherever you see 3 to the x, you rewrite that with u. So what if I have u instead? This will be u squared minus 12 times u plus 27 equals 0. Now for the time being, this equation that I've just rewrote looks like a quadratic. It's a
Mhm.
quadratic. This is a quadratic function. Quadratic function with variable u. Now what can I do here?
You can double bubble.
Double
U,
bubble. And I get what?
U, 9 and 3, negative, both negative.
U minus,
3 and U minus 9.
okay. And then
And then
u
U
equals
equals 3,
3.
U equals 9.
But what's the original variable?
Oh, it's the original variable is 3x. 3x
Right. So
equals
let me, yeah, let me
9
just
and
let me just rewrite these with the blue color. So then you start to see that this is the substitution that I made, but that's not the original variable. My original variable is x. So then I rewrite using the original variable, which means that 3 to the x, that equals 9. And 3 to the x, that equals 3. So then what can we figure out? What does x equal here and what does x equal here?
x would equal 1
On
on
the
the
right
right,
side.
on the right side.
That's right. X equals 1. And then what does x equal on the left side? 3 to what power gives me 9?
3 squared. So you
3
got to
squared.
write it as 3 squared, and then x would equal 2.
X will equal 2.
Okay.
There you go. You have two solutions. X equals 1 and x equals 2. Okay?
Yep.
Does this make sense to everyone?
Yeah, it's not that bad.
Not that bad, right? Yeah, this stuff isn't as bad as the other things that you may have seen. Okay? Okay. Any questions about this? Now, let's briefly go over this. What if I want to sketch the function? Um, let's write this as yeah, 3 to the negative x. What is this function? First of all, is this exponential growth or exponential decay?
Would you say
Is this exponential growth or exponential decay? Decay. And why is that? Why is it a decay? So you're right. It is decay. But why is it a decay?
Because it's less than 0.
What's less than 0?
The x.
No, it's not. It
Oh,
has nothing to do with the x.
the base is less than 1.
The base, yeah. So even though you see 3, right? You can rewrite it. So you guys
One-
are very good. You guys are very good.
It's 1/3.
Right. You can rewrite this as 3 to the, if you want, right? You can write this as 1 over 3 to the x, because that's what you do when you have a negative exponent. And then you can rewrite this as 1/3 raised to the x power. So that's crucial, guys. When you have a negative x, you can rewrite that as a positive x, but now the base is a fraction. And then this fraction here, this b here is 1/3, which is less than 1. So it is a decay. It is an exponential decay. Okay, good. So you guys understand that. Okay, great, great. So exponential functions are usually the easier ones to deal with. And now we're gonna head into a logarithmic function world. Does anybody know what logarithms are?
Something to do with base 10.
It can deal with base 10, but not part only with base 10. That's a good one though. It does include base 10. What else? Anyone else?
All I remember is like natural something, like log 10 and a whole bunch of like letters in 10.
Good. Good. So actually the word logarithm means exponent.
hmm
Do you guys know that? This actually means an exponent. So that's kind of strange because you're like, wait, but we just talked about exponential functions. Why are we talking about logarithmic if they also mean exponent? Well, consider this, okay? Consider this. So, for example, if I say 2 to the 3rd power, right? This equals 8. We know that. This is called an exponential form. We have a base, right? We have an exponent, and we have the result. So this is like the mechanism. We have a base here. This is my base. This is my exponent. And this is the result of exponentiation, right? This is the result of exponentiation. Now, logarithms are the same exact thing. They're just expressed differently. Does anybody know how I can express this in logarithmic form? If not, that's okay. But logarithmic form, what's the base of the exponential form?
2.
2. So what's going to be the base of my logarithmic form?
2. So it'd be log
2.
2.
I'm gonna write it like this. I'm gonna write log, right? I'm gonna write using these 3 letters, log.
Subscript, I think.
And my subscript is 2.
hmm
So they match, right? They match. This is my base. Now the difference, though, the difference, there's a structure. There's a structural difference. And Coco, yes, that's right. This is log base 2, right? And then I rewrite this as parentheses. So let me just say, this whole thing is the name of the function. The function is called log, or the logarithmic function with base 2. Now, what this results in is the exponent. This is the exponent. This is the exponent that you find here. And the input is 8. So do you see how I rewrote this? In exponential world, 2 to the third power equals 8. In exponential world, we're saying, give me what is the exponent for the base 2 to give me 8. Well,
That's
we
3.
just said it. 2 to the third power is 8. Henceforth, log base 2 of 8 is equal to 3. Do you guys see that connection?
Mm-hmm.
It's just another way to express it. So let's do more of these. So let's say I have like 5 to the negative third power, right? This equals 1 over 125. That's exponential form. How would I write this in logarithmic form?
Log 5,
Log base
125,
5, and then you plug in what into the parentheses?
1 over 125,
1 over 125. This equals
-3.
perfect. That's all it is. So in a way, you can think of it as switching the x and the y. So in general, right? In general, if you have y is equal to b to the x power, I can rewrite this as saying x is equal to log base b of y. So in the way, the x's and the y's are swapped. So you can think of it as x and y are quote unquote swapped. So that gets interesting. That gets interesting pretty quickly. So let's compare the graph, okay? Let's compare graphs of y equals 2 to the x and y equals log base 2 of x. So we already know what this looks like. We have a function that looks like this. It's growing. Crosses it at 1. Y, x. Now, what's the difference between logarithmic functions and exponential functions? Remember what I said, x's and y's are swapped. So if you have x's and y's swapped, if x and the y values are swapped, it's the same thing as saying you reflect. There's a reflection across the line y equals x. So if I got the line y equals x and I reflect it across that line, I get the logarithmic function. So think about reflections. So if you cross it at 1, if you cross the y axis at 1 for exponential functions, you're going to cross the x-axis instead at 1 for logarithmic functions. Do you guys see that? So
Yes.
logarithmic functions have a different graph, but related to the exponential function. And they're just reflections across that line y equals x. It's like a diagonal line through the axis. If you just reflect it across that line, you get the logarithmic function and vice versa. So I'm just wondering, is this new stuff to you all, or have you guys seen this before?
We've definitely seen this before.
Definitely seen
This-
it.
Yeah, this was in like college
Okay.
algebra.
Okay, good.
Yeah, high school too.
Yeah, high school they talked about logs. Okay, good. Great, great, great. So this is a good review. All right. And since you guys have seen this before, what are the laws of logarithms?
I don't necessarily remember the laws, but doesn't have to do with like how you can rewrite them in different ways. And like
Yeah.
if you have two logs with the same base, you can just drop the log, something like that.
If you have
Or-
two
or-
log, so the thing is, if you have log of a certain base, right, and you have x times y, do you know how to rewrite this?
Would it be? Would you just write it as two separate logs, like log b x plus like log by?
That's right.
Yeah,
That's right. That's the sum rule, and then you have log base b of x over y. This becomes what?
it's the difference rule. Like I'm
The
guessing.
difference rule, right? Log base b of x minus log base b of y. Good. And then what if I have log base b of x to the y power? This is the power rule. How can I rewrite this?
I don't remember that one.
Does anybody remember? Well, the power rule states that you can put this exponent in front. So I can rewrite this as y multiplied by log base b of x.
Oh,
That's the power rule. And then what if I have log base b of 1? What is this equal to?
isn't it equal to the base?
Remember what this logarithm means. It means what is the exponent that I have to raise? What is the exponent that I have to raise b, the base, so that
0,
I get 1?
0.
0. Log base of any base of 1 is 0 always. And then the next
Log base of what
1
is it? So log base of 1 is always 0.
always, because
Okay.
why? Why? Because b to the 0 is always 1. That's the same reason. So
Mhm.
because b to the 0 is 1, log base b of 1 is always 0, interchangeably.
Mhm.
These are the same thing. We're saying the same exact thing,
Okay.
just in different order. You can think of it. And then what's log base b of b? What's log base b of b?
1.
1. 1. Why is that? Because b to the first power is b. What is log base b of b to the x?
X.
It's what?
No. Wait. Yeah, X.
X. Okay, good. 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 Okay. You guys are pretty good with this. I'm glad. So let's see this. What is how can I express express the following in logarithmic form. Express the following in logarithmic form. So I want to express this as in logarithm. So what if I write 32 to the 4/5 equals 16? This is the exponential form. I want to write it in logarithmic form. So what would be the logarithmic form of this?
Log base 32, 16 equals 4/5.
Perfect. What if I say 16 raised to negative 1/4 equals 1/2?
It's log 16 1/2 equals negative 1/4.
log 16 of 1/2 equals negative 1/4. Good. Good, good, good. What if I say e what if I say e to the negative 1 is 1 over e? Hmm.
It's like the same exact thing.
What is that same exact thing?
I thought log of e was like different. Like, what? I'm not sure. Is it the same format as before, or is it
Yeah, the format
different?
doesn't change. Doesn't change.
Oh, okay. So then there would be log e of, yeah, log e, and then 1 over e equals negative 1e.
Negative 1, not negative 1e.
Oh yeah, negative 1, negative 1.
That's negative 1.
Mm.
But we don't say log e, right? Santiago, we say ln. So this actually, we rewrite this and say ln of 1 over e.
I knew it was something different. I knew it was something different. I was like,
So these are the like the special logs, okay? These are special logs. Special logarithms are based upon their base. So the first one is the natural logarithm. Natural logarithm. They call it natural logarithm because the base equals e. Oh, I should write this. The base. So then if you have like y equals log base e of x, this is really y is equal to ln of x. Okay? So like for example, if I say ln of 3 equals x, how would I rewrite this in exponential form? What would be the exponential form of log 3 equals x? Well, what's my base? Natural log. My base is
E,
e. What's my exponent?
X,
X. E to the x equals
3.
3. So ln natural log. Okay? And there's another one. There's another one called the common log. Does anybody know what the common log, what the base for the common log is?
is it 10?
It is. So then if I say y is equal to log base 10 of x, I'm not going to write base 10 because it's so commonly used. So I'm going to say just log. So whenever you just see log regularly, it's base 10. Whenever you see ln, it's base e. If you see anything else, it's usually specified. So log base 2, you see the 2. Log base 3, you see the 3. Log base 7, you see the 7. But log just regularly, you don't see the 10, common log. And the e, you don't see it as well. You see ln. So you should be able to recognize that. Okay. Okay. Now, I just want to make one note as well. Another note. Note is that the a logarithmic function is undefined
No.
for negative input values. So for example, you cannot say log base -2. This is undefined. Log of -2. There is no number that you raise 10 to that gives you a -2. So there is no number. It's because 10 raised to what equals -2? There is nothing. There's no solution. There's no solution to this. There's nothing that you can raise the 10 to a certain power that gives you a negative number. It's not possible. So logs can produce negative numbers. Log cannot receive negative numbers as inputs. Okay? Just want to make that clear. Okay, so let's play around more with some logs. So what if I want to combine into single logarithm?
Isn't that just the like kind of the reverse of the laws that we were doing before?
Correct. So like let's say if I have like a ln of 2 plus 1/2 ln of x plus 1 minus 2 times ln of 1 plus square root of x. What if I want to put all of this together
So
into a single log? Anybody?
times
What kind of powers do I need here? Does anybody know?
so would you so they would all technically have the same base of like e, right?
They would, yes.
And since it's addition for like the first two, would you multiply the first two, and then since it's subtraction for this, is that subtraction?
Yeah, so first thing I would do though is to take care of the numbers in front.
Yeah.
I'm gonna
Okay.
put it inside, right, using the power rule. So this would be equal to what? This is ln of 2, just regular. This will be ln of x plus 1 to the 1/2 power minus ln of 1 plus rad x to the second power. So
Mhm.
all I did was I applied the power rule. And
Yeah.
then you said correctly, right? This is a plus. So then you would have to multiply the inside here. So this would be ln of 2 multiplied by x plus 1 to the 1/2 power minus ln of 1 plus square root of x squared. Correct?
Yeah, and then you're going to divide by
And
this
then this
second
is
half.
2 times the square root of 1 plus x. Let me just rewrite these to the 1/2 power. I'm going to rewrite it as square root. And this is ln of 1 plus square root of x squared. No, I cannot distribute the 2 as a square. I cannot. I would have to expand everything. I'm just going to leave it this way. And now this is subtraction. So this would be ln of 2 square root of 1 plus x over 1 plus square root of x squared. So that's how you combine into a single logarithm. You apply the rules of logarithms and go backwards. Easy enough?
Not really.
No?
In theory, it's simple, but to actually do it on your own, I'm definitely gonna get lost.
You're gonna get lost? Oh, don't
Mhm.
get lost. Don't get lost, my friend. You need directions.
This is
So
gonna be on the final.
this may be on the final. Yeah.
Okay, I'll take the L.
No, don't take no L's. Why you want to take L's?
Professor, you have not seen the final yet?
Well, I have not created the final yet.
I thought
Wait,
it was
so if
I
you
thought it
didn't
was
create
like
the
a.
final yet, can't you just tell us what's gonna be on it and make
Huh?
our life, I don't know, a little bit easier, so we don't have to take L's?
Yeah, Professor, I would love if you could just like, you know how we have all those review sheets and everything. You were saying like before that there's like 6 problems per like each like type of like
Topic.
section.
Yeah.
Yeah, like per topic. Like if you could just like star like which topics are the most important for the final, that'd be wonderful.
Okay.
Professor, have you graded the last exam yet?
Professor.
I haven't completely graded it. I said in the beginning that I plan to give it back by tonight.
Professor, just a quick question. When does the quiz start?
I'm planning to make it at 9:35 so that you guys have 10 minutes. I mean, not 10 minutes. You guys 20 minutes for the quiz.
All right, cool. Thank you.
How many questions is the quiz?
It's only going to be 3.
Oh man.
It shouldn't be that.
Is it gonna be a word problem like we were doing like last week?
It's a very short word problem. Let me just say that. It's like a sentence long.
Oh, okay. And it's three separate word problems.
No, it's actually 2 problems. You'll see. It's 2 problems that yeah, they're all one word, one sentence problems.
Okay, so they're not as complex as the stuff we were doing before.
I would not say they're as complex. No.
Okay, great.
I would say the first 2 are straightforward, and number 3 is what you have to do a little more thinking. A little bit. Right? That's what we love to do. We love to think, don't we?
I like to follow a recipe.
So you like the cookbook style things, huh?
Yeah.
Yeah.
Right.
Okay, so let's do one more of these just to get our feet wet with this. Now what if I get something like this? ln of let me use this. How about log of 3 plus 1/2 log of x plus log of y minus 1/3 log of z. What if I want to combine all of this into a single log?
So you're gonna
So
have
you,
to
uh-huh.
you're gonna have to undo all of the like the 1/2 and the 1/3 that are in front of the logs.
Yes.
So you're gonna rewrite that
So I'm plugging it back in
as
here.
yep.
And
And
then I
then
get log of 3 plus log of x to the 1/2 plus log of
y
y minus
minus
log of z to the
logs 1/3.
1/3. And then I have
Now,
all the pluses here, right? So the
yep,
pluses are going to be combined by
multiplication.
multiplication. So I get log of what? 3 x to the 1/2 y minus log of z to the 1/3. Then have subtraction. So now I can write this as one single log as log base. Log of 3x to the 1/2 y over z to the 1/3.
Yep.
And then I can use radicals. This becomes 3 square root of x y over the cube root of z.
So the exponent rule that we learned for the like the derivative stuff works here too.
The derivative, no, there is no derivative here. So
Wait,
we haven't talked about derivatives yet.
no, but I'm saying like how you rewrote the x 1/2. That's not a rule that's specific to derivative. That's just in general for any
That's just
exponent.
in general with radicals, fractions, yeah. X to the 1/2 is square root, x to the z to the 1/3 is the cube root.
Yeah, so we learned that with derivatives. So I just assumed that was just like
No, you
a
learned that,
derivative based rule.
or you should have
So-
learned that in 115, math
Oh yeah.
115. Yeah, this is this is an algebra. This is just an algebra
Law.
laws of like a algebraic technique, algebraic function. As that's used, it's used for derivatives,
Mm.
but it's not derivative based.
Okay, I understand.
Okay, so now, so quickly, since this is combining into single logs, what if we want to expand? What if we want to do the opposite? Expand logarithmic expressions. What if I want to expand? So let's say I have something like this. Um, log of the square root of x plus 1 all over x squared plus 1. What if I want to expand this? So I want to just go from a single to an expanded form. What would this look like?
So you could start off with subtracting
Right.
the bottom from the top and separating the logs, and
So
then
separate the fractions by writing it as log of the numerator, which is the square root of x plus 1,
Mhm.
minus log of the denominator, which is x squared plus 1, correct?
Yep,
And
and
then,
then you can rewrite the like the square root as
yeah, I
like
can rewrite the square root
as 1/2,
as x plus 1 to the 1/2 power
and
minus
then
log of x squared plus 1. And then I can do what?
you can take the x squared and the 1/2 and move those to the front of the logs.
I can only take out the 1/2. I cannot take out the x squared.
Oh, because it's attached to one individual thing. Okay, I
Correct,
see.
because the square only is attached to x, not to the 1, and there's a plus in between, and there is no rule for that. I don't have a rule for that. So I actually just leave it. And this would be minus log of x squared plus 1. That's it.
Yeah, this is not as bad as the other stuff we were doing last week.
Well, I mean, I guess different strokes for different folks, right? Some people say this is not that straightforward. Other people do. So let's do one more. So how about ln of x squared divided by the square root of x 1 plus x squared. So I want to expand this.
It's the same format as before. You separate them through division, so it's subtraction.
So ln of x
X
squared
squared
minus ln of the square root
x.
of x 1 plus x squared, right? So this is the numerator and denominator. And ln of x squared, you see this 2 here? I can place it out in front and I get 2 times ln of x. And now here I have a what? A product. So then I have to be a little careful with this. This becomes ln of square root of x minus ln of 1 plus x parentheses squared. And this is going to be a plus part of me.
Yeah, I was just about to say, shouldn't this be addition?
It's a plus because eventually though, this -1 I'm going to distribute, and this will be now 2 ln of x minus ln of square root of x minus ln of, and there's a 2 in here too, so I can place this out. So this becomes -2 times ln of 1 plus x. And then this square root of x, I can rewrite this as ln of x to the 1/2 power. So then I can take out the 1/2 in front. And so finally my answer would be 2 times ln of x minus 1/2 ln of x minus 2 ln of 1 plus x. And actually I can combine this further. 2 ln of x minus 1/2 ln of x is actually 3/2 ln of x. I can combine like terms. And this will be my final.
Why didn't you also take the minus 2 on the other side, is that because they were on the opposite sides of the subtraction?
Say that one more time.
So you see, you took the 2 and the minus 1/2, and you combined them, right?
Yeah.
And did you also combine the -2 in front of the ln?
No,
Why not?
because they're completely different. ln of x is not the same as ln of 1 plus x.
Ah, okay.
ln
I
of
see
x
that.
is the same as ln of x. So then it's like saying, hey, you have 2 apples minus half an apple. How many apples are there? There's 3 half apples left. But this is
Mhm.
an orange. It's not an apple. So you
That
can't
makes sense.
compare apples and oranges, as they say. Right? So any questions about these techniques of logarithms?
Nope. If we're done, can we set the quiz early?
Oh, we're not done.
Okay. I just wanted more time.
Don't worry. I think you'll have enough time for this. There's only 3 questions. Usually I give you 4. So I give you 1 less. So you have more time, actually. Hopefully. Okay.
Professor.
So, yeah.
So for ln, the base is e.
Yes.
Okay.
Always and forever.
So even though they have the same base, you still wouldn't combine them because.
Okay, so they have the same base, but the functions themselves are distinct. ln of x is completely distinct from ln of 1 plus x. Sure, they have a commonality that their bases are both e. But if I were to graph ln of x and compare that to ln of 1 plus x, they're 2 different graphs. So they're 2 different functions.
Okay.
Okay. So I've mentioned all of this as more of a review, right? Well, I'm glad most of you felt. I mean, hopefully, I haven't heard from most of you, but I hope that most of this is a much of a review of logs and exponential expressions. Uh, and why do we even bring this up? Is because we need to know how to take derivatives of exponential functions and logarithmic functions. So let me show you what that is.
Yikes.
So the derivatives actually aren't as hard. So these are just additional differentiation rules. For exponential and logarithmic functions. But in particular, we're going to be discussing natural exponential and logarithmic functions. Natural. So they're very quick. They're very quick, guys. It's pretty interesting. The derivative of e to the x, this is an exponential, a natural exponential function. Why is it called natural? Because you have e as your base. And guess what the derivative of e to the x is? Look how hard it is. It's e to the x. This is very interesting that the derivative of a function is itself. You don't see that every day. So that's it. The derivative of e to the x is e to the x. Any questions?
Yeah, how come it's not just plain e? It looks like you didn't do the part with the minus x. The -1.
Because the power rule only works for power functions. Power functions have this form.
Mhm.
X to the n. N is not an exponent. I mean, n is not a variable. N is a number. X is the variable, right?
Ah,
But in this case, we have e to the x, where it's the opposite. This is the number, and this number is 2.718, and this is the variable. So we cannot apply the power rule to exponential functions because it's not a power function.
Okay, that
It's
makes
different.
sense.
It's
So,
different. And it's just interesting to notice that the derivative of e to the x is indeed itself. That's just like interesting because any other function becomes completely different. If you take the derivative of x to the 100th power, it becomes 100x to the 99th power. It's just a different function. In this case, e to the x remains. If you take the derivative of it, it remains e to the x. That's pretty cool. Now the next one is, what's the derivative of ln of x? I mean, sorry, what's the derivative, not of ln, what's the derivative of 1 over x? No, actually, no. Yeah, what's the derivative of ln of x? So the derivative of the logarithmic function that's x but has an e base of e is actually 1 over x. So the derivative of ln of x is 1 over x. The derivative of e to the x is e to the x. So
is
let's
this something that we should just know, or
yeah.
is there like an explanation?
So the explanation, that's a good question. How in the world is that true? Do you see that? So then here we come, we come to a dilemma that we sometimes encounter, particularly teaching mathematics. Sometimes we don't, what is better? Is it better just to know the formulas and move on with your lives? Or is there a need to justify every statement that we make?
Mhm.
So to justify these things, you need a bit more of advanced understanding.
Okay, so for now,
So
it's
for now,
just
it's perfectly fine just to be like, yeah, okay,
that's what it is. Okay.
that's what it is. But really, the more interesting question is what you raised: is why? Because these kind of seem strange, doesn't it? Like e to the x, the derivative is itself. You're like, what? Okay, and then the derivative of ln of x is 1 over x. That's like, wait, how does 1 over x connect with ln of x? Why is there a connection of this sort? And why is e to the x connected to itself when we talk about derivatives? Those are interesting questions to ask. And of course, there's a reason for it. In mathematics, they're not going to be telling you something that's true without having basis for it. So that's what makes mathematics a very interesting subject, because everything that we say that is mentioned, for the most part, has a justification for it.
Mm.
Everything. Especially at this level, everything has a reason. There's a rhyme and reason for everything. And this is when you can use Google to your
So,
advantage, right? And be like, hey, why is the derivative of e to the x, e to the x?
so
And of course,
Professor,
yeah,
for the first example you gave us, like the derivative of e to the x equals e to the x, you're basically telling us that the instantaneous rate of change is constant throughout the whole
no,
function.
no. I'm not saying that, but that's a so you almost said the correct statement. I'm saying that the derivative of e to the x at every moment, the instantaneous rate of change of e to the x at every moment can be found using itself.
It's almost like we could do this for a little extra credit.
That's a good one, Andrew. That's a good one. A little extra credit.
Yeah, if we just figure it out, hand in a little thing.
Had the little thing, a little 5 points here, a little extra.
Never hurts.
Do some fries on the side, and then
Never hurts. Never hurts.
oh boy, oh boy. The extra credit, um, extra credit. People love extra credit. It's amazing. It really is. I'm
It's just
amazed.
more opportunities to learn.
Hey, you're a good salesman. Let me just say that. Okay, so really quick, if I want to find the derivative of something like this, e to the negative x squared, guess what we're going to have to do? So we know that e to the x is e to the x because it says in your textbook, e to the x, the derivative of e to the x is e to the x.
Mhm.
How does that, what is that relationship? How does that relate to what we have here, e to the negative x squared? So this is when you have to apply the strong and powerful chain rule. Remember the chain rule? The chain rule says find the derivative of the outer function, multiply it by the derivative of the inner function. So the outer function is e raised to some power. But we already know what the derivative of e raised to some power is. It's e raised to that same power. So then the derivative would just be e to the negative x squared. But hold on your horses. You have to find the derivative of the inside function. What's my inside function? Negative x squared. This is my inner function. And this thing out here is my outer function. So what's the derivative of negative x squared? Power rule. So this becomes negative 2x. And so then my final answer is negative 2x e to the negative x squared.
Professor.
Yes.
So when you took the power, when you took the derivative of e, it just e.
Yeah.
Did you got ex?
E to the negative x squared. It's like saying you leave that function the way it is. Just leave it.
Okay, so that's what you did. Okay.
So derivative of e to that power is equal to e to that same power. That's what I'm saying. However, that power is a function itself of x. So you have to account for that in using the chain rule. So the chain rule here was used. So derivative of e to negative x squared, the result of it is going to be e to the negative x squared, but then you're going to tag along the derivative of negative x squared, which is negative 2x. So the final derivative is negative 2x e to the negative x squared. And that's how, for the most part, this will go. Okay? And we're going to continue with some of these examples further in next class. And just quickly, what if we have g of x of ln of 5x, for example? Well, the derivative of ln of x is 1 over x. So the derivative of g prime of x here, the derivative of ln of 5x will be 1 over 5x, right? 1 over whatever's inside. That's another way to think about it. Ln of whatever that thing is equal to 1 over that thing, which is here in x. In this case, that thing here is 5x. So ln of 5x is equal to, the derivative is 1 over whatever is inside. But then I have to do what? Multiply by the derivative of the inside, which is 5x. What's the derivative of 5x? It's 5 by the chain rule. And so the 5s here cancel. So actually the derivative of this function is also 1 over x. Now that's interesting too. The instantaneous rate of change of a logarithmic function, natural logarithm function is 1 over x. Interesting. Yeah, there's different ways to prove this. There's different ways to prove this is true, and there's different ways to prove that this is true.
Professor, why did we cancel the 5s?
Because you have a 5 in the denominator and you have a 5 in the numerator. the 5 in the denominator came about because you took the derivative of ln, which is 1 over the input, which is 5x, and you got the 5 in the numerator because you apply the chain rule.
Oh, the inner function.
The inner function is the derivative of 5x is 5, so then that 5 appears in the numerator, but the 5s are canceled because you have one in the numerator, one in the denominator.
All right. Yeah, makes sense.
Okay. So not that bad, right?